Welcome to the afternoon session. Great to be here. And I couldn't be happier with our keynotes. So now, everybody is doing intent-based networking. So the question is not whether, the question is when. And I'll be referring to what you've seen this morning from Bikash, probably a lot, because it makes sense. However, from his presentation, intent-based networking is this magic box, black box. You put your intent and it does networking. So my intent, no fun, is to explain what it really does, what the industry is doing about intent-based networking, and how it can be implemented. So why intent-based networking? Traditionally, network management has always come as afterthought. I mean, all of us who grew up on networking, we are CLI people, right? Till today, a lot of stuff is done without really thinking about networking as a distributed system. We still have box view. We still think about features per box rather than system-wide behaviors. So we really need to change things. Network automation is a mandatory feature given the scale, the complexity of today's networking. Right? There's no way around. It looks pretty familiar, right? Everybody. So we've been trying to do some stuff about management for as long as I remember myself. SNMP wasn't such a big success. We started young effort about 7-8 years ago. Today we are 250 young models in ATF, probably another 150 in other SDOs. Stuff still doesn't work together. Probably Anis is here, OpenConfig, there are other people. You get some parts here, some parts that don't correlate, they don't work together. So we need a layer that will normalize, that will take business logic and instantiate networking, and really abstract the difference between models, between whatever you use to instantiate your networking. This is actually a very important picture because you see that intent-based networking landscape is growing. There's many companies, some claim, we call it intent washing, right? You really need to have full view from design for intent consumption to intent instantiation in order to be able to do it. If you only do forwarding, if you only do control plane, if you only do pieces of management plane, all you see, it's a fan, it's a rope, it's a wall. You don't see network as a distributed system. It's a fundamental for intent-based system to do all these phases. So if you look at today's landscape, we define 4 levels. At basic automation stage, we're really talking about configuration. And I think it's a pretty solved problem today. We've got on the scripting tools, Ansible, Chef, Puppet, all those tools that are open source. They're usually multi-vendor and give you ability to configure devices pretty well. On another end of the spectrum, you've got really vendor tools, ACI, Cloud Vision. They work really well with this particular vendor. However, you are locked to the vendor, and this is the intention, right? So given that the problem is solved, the level 1 is having ability to have this entity that's called single source of truth that is the source of intent for any layer in the intent-based system. I will be talking about it throughout my presentation. What I think is really most complex part is ability to deal with changes. Network change all the time. After 2 seconds, your green field becomes brown field. How do you deal with the changes? What they mean? How do you reconcile them? How do you bring your network back to intended state? It's the most interesting part and most complex part building an IBM. So in terms of standardization, we've started some work in RTF. There's a draft that has been adopted. It defines number of fundamental building blocks. And building right vocabulary is important. When we talk about things, we need to make sure that the meaning of things is the same, right? So single source of truth, it's a fundamental functional block of any intent-based system. What it does, it takes business logic, northbound, normalizes it, and makes southbound networking vendor independent, or vendor agnostic in other ways. So it doesn't really matter who your vendor is, as long as you can translate business logic into something that could be consumed and configured. And we have always focused on configuration. It actually doesn't really matter whether you CLI, netconf, some layer of APIs, as long as your logic could be transformed into networking, anything does the work. Another important point, and we talked a lot about telemetry, right? If you look at the amount of telemetry modern device generates today, we are talking about terabytes of data. So we are creating just yet another data lake where all this data sits and no one actually looking into it. Some do, but very little. I think where we really need to go is to ask real questions. We need to ask, give me data that's actionable, that's actually of importance to me. Since I define the intent, I know what my service is, I know exactly what data needs to be there. And if dropping 1% of my packets is okay, I probably don't want to know about it. So defining data that you need to get back from the system in order to validate intended state is mandatory. Otherwise, we end up again in terabytes of data, and you need to build out-of-band networks that's probably more expensive than your on-band network. Another very important point, I'm going through what we are trying to standardize in the draft, is really need to decouple policy definition from policy enforcement. Policy definition is a business logic definition saying user A cannot talk to user B. Whether you instantiate it as part of your IP tables, ACL on the switch, knuckle, ACL on public cloud, it's not important in terms of definitions. So decoupling these 2 points is really mandatory for intent-based system to scale and be multi-vendor, multi-purpose, whether you want to use it on your switches or public cloud or SD-WAN. So why data center is a good starting point for IBMs? Ability to reason about your state is most fundamental property of IBM. At any given point in time, you need to understand state of your system. It's a distributed system. It is complex. It has many different states. Ability to understand what it is fundamental. Luckily enough, in data centers, I think we pretty much all converge around leaf-spine architecture, close. The great point to this topology, they mutate in very predictable ways. Whether you have 4 switches or 40,000 switches, the connectivity patterns, the directionality is exactly the same, which is perfect for IBM because independently of size, number, and variety of devices in your network, the end result, the expectation is exactly the same. You know that leaf switches have to connect to spine switches and must not have any links in between, right? And again, if you build layer of super spines or 5 or 7, 9 stage network, it doesn't really matter. The expectations are exactly the same in terms of connectivity, in terms of how your routing should look like, in terms of how your next hops in your routing update should look like. So by only defining my network is leaf spine, you already have 90% of what your network is going to look like. You know what to expect. You can reason about its states. So Telco 1. I mean, we've all seen day 0 when you start from scratch, you build this beautiful thing, and then day after tomorrow you look and you see day 2. As we said before, ability to reason about why your network is in particular state is fundamental to ABN. In Telco, we are not yet there. There are pretty much no practices. Every network looks different. They're all snowflaking. However, there's a hub. In IETF, we've been doing really great work. There's RFC8453 that defines number of interfaces, that gives us ability to build pretty much intent-driven logic. Customer defining what network should be, having 2 interfaces that are communicating with another layer of controllers that are configuring the network. So there's a good foundation, and for a second, having head of there's a design team working on network slicing in IETF. I've been part of it. Intent-based networking is a perfect candidate to provide network slicing, because now we are talking about 3 completely different domains, being packet core, being xHaul, and being really transport below. The way you can express your logic is really high level. So you can say, I want particular latency, I want particular jitter. So someone has to take this information that's really high level and translate it into exact networking. That could be an LSP. That could be something that's really related to networking technology. So looking at what we do for 5G, for network slicing, it looks like intent-based networking is a perfect technology here because we need to normalize state. We need to provide single source of truth that any system that is consuming it is able to take, understand, and build. This is the last slide where I talk about complex things. So what's IBM really? The design philosophy is to tell the system what do you want, not how to build it. And this is fundamental to the system. You express your logic. Your interface or not-bound API should be expressive enough for you to express the logic, but this is it. You're not asking for VLAN. You are not asking for a CL. You're expressing your logic, commonly known as business logic. So, and again, we published a draft that explains in great details what those are, the relationship between policies, autonomous networking, to intent-based networking, and how things work together. So, life cycle. And we will see why it's so important to have this particular order. So, as you could see, we start with intent consumption. So, someone has to tell the system what is it you want. It could be OSS BSS layer, it could be a workflow user goes through, it could be any system that can express their intent. Then we need to build the logical model of what we are trying to do. Why logical? Because device is not important. We are much before we are going to tell it's going to be Juniper or Cisco or Arista, right? It's just a device that has particular characteristics, 32 100 gig ports, for example. When we go into deployment phase, however, now you need to understand the semantics of the devices you're going to be dealing with. This is where input from user, or at least some inventory, is important. So someone has to tell you, this switch is Arista, this switch is Cisco, those are the characteristics. So there are two ways really to create workflow. On one side, you could just feed your inventory. On the other side, if you're really going intent-driven way, you could say, I've got 100,000 servers that I need to be connected. Please tell me how many switches do I need. I need segmentation. Probably I need EVP and VXLAN. Tell me which switches support this functionality. So thinking about software before you actually think about vendor and hardware is really the way to go. Because if you've already deployed your hardware, probably you would need to somehow adjust your expectations, and your agility in terms of service delivery is becoming limited by what you have already deployed. So ideally, you should first think about your management plane, and it should really tell you what to deploy. Validation phase starts immediately after deployment. So it's not an afterthought. When you design your network, you already know what you're going to be getting. So most of the expectations can already be created. So when you hit a button and say, create networking, this red magic button, immediately you need to know whether what you actually expect from the network is what it should be. So in other words, your operational state should be same as your intended state. And anytime there's deviation, you go back, you either remediate or you let user know, something isn't working, go and fix it. So having this closed loop validation, and you've heard about this whole day, right? It's mandatory for a system to work, any distributed system, not just networking. You need to know at any given point in time what's going on in order to remediate. So high-level day in life is what you need to have is this normalized layer that's really sub-pub infrastructure to provide information to consumers that are lower, so southbound devices, switches, networks, and being able to consume business logic, being through API layer, being through user interface. So any way business logic could be communicated to you. You want to have it vendor independent. This is kind of the goal of intent-based system. It's not about vendor, it's about functionality. Vendors are secondary to the functionality. So when you model your network, you think about logical models. It's a logical switch with 100 ports. It's a logical device that's a firewall. Right? Much later, when you decided what it should be, you go and decide, I'm going to put Palo Alto firewall there and Cisco switch another place. Right? And anytime you do this, the beauty, you don't have to deploy stuff to actually validate that what you've done is right. Since you built full logical model, you could run analysis saying, this is what I want, this is what's going to be, is it really my intent? So system will tell you, you're trying to do A, you're getting A plus or maybe B minus. And this is how to remediate it. The ability to compare states is, again, fundamental to an IBM. So in all good days, when we were writing this book with Ross White, I2RS started in ATF, and world looked beautiful. We all expected networks to be programmable, have these beautiful interfaces. But in definitions, we said that network is programmable when it could be programmed through data-driven APIs and expose all needed interfaces, being what device is capable of, what has been consumed, so inventory, topology, so the connectivity map, connectivity graph, and telemetry. We said you always need to know where you are. So this is a picture from 2014. Now in 2020, we are still nowhere. We've seen vendor implementing some service-level APIs. There's great work on the OpenConfig side, providing GNMI, gRibi, number of other interfaces that unify the data, but still, we are nowhere. There's no single way to configure system through machine-to-machine interface. So at the end, what you want is a fruitcake, right? However, to build it, you need many different things. And fortunately or unfortunately, not all of them are comparable. So, you're getting get the data over net flow. You've got some RIP states. And when you try to configure stuff, correlating your existing data to what you're trying to do is not straightforward. So data normalization, ability to reason about data as such, is mandatory to be able to deploy anything at day 2. Again, basic configuration is easy because there's no state. You go from 0 to S state. When you try to move your graph from A to B, this is where things become really complex because you don't want to break anything and you want to be agile. You want to be able to deploy as business requires. So this data normalization in single source of truth is a mandatory part of any intent-based system. So let's look at architectural goals and what needs to be solved. We'll be talking about composition, decomposition, and scale. And again, as you've seen in the Google talk, you get an optic that has MTBF of 50 years. You deploy 100,000 of them, suddenly it fails every 2 hours. So scale counts. How do you deal with changes? Can I deploy a change on a particular network? Going back to Google, imagine someone would have told, actually, you cannot reload all network systems at the same time. We wouldn't have 6 hours outage. So ability to plan change according to business logic, according to a security principle, according to what people in charge have decided is very important. So again, reasoning about your future state without actually getting there. Unplanned changes, network change all the time. Things break, things go down. So ability to define, is it relevant? Does it affect any customers? Which customer does it affect? How do I remediate is fundamental for a system. Closed loop validation. So ability to continuously validate all the changes in the network is necessary in order to be able to decide whether change is relevant, whether you need to react, or you can just ignore it. As we said, there's so much data that's coming from the network. If we try to consume all of it, we are going to be just thrown in data lake. So we need to know what questions to ask, which data to get, and how to decide if data is actionable. And optimize the scenario is important. If you have 5 interfaces that are up, why do you need counters from all hundreds of them? If you don't run BGP, why do you care about telemetry from BGP? You need to ask the right question. And you've designed your network. You know what to ask for. Just do it. So what you see is 16K network with all the attributes. This is a graph picture that shows really the complexity of relationship. What's composition? Basically, you take simple functions and compose them into one more complex. On a separate note, why do we model networks as graphs? Because they are graphs. Networks are interconnected graphs. Why particularly graph databases? Graph database consists of nodes that have particular attributes or metadata attached to them and relationships. If you look at networks, they are databases, or their databases are exactly the same. They're interconnected nodes that have interconnected links that have particular attributes attached to them. The beauty of graph databases, you could always craft a graph query that has this additional piece of metadata that lets you know exactly what you want to know. And we will see further how it can be used. For part of this presentation, any further slides are going to be related to this network. So how do we model how graph is composed when you have the simple network with 2 spines and 4 leaves? You've got spines, you've got interfaces on the spines, links that are coming out of those interfaces, interfaces on the leaves, links, and hosts connected to it. So what you see is really graph representation of your network, where you have nodes, hosts, leaves, spines, and links that connect them. There's a lot of metadata attached to them, and we will see how this metadata could be used in order to ask right questions. So this is a schema of exactly the same picture seen before. Since we are building leaf-spine network, we make some assumptions. We know it should have some spines, it should have some leaves, it will have some hosts attached to them. Since it's leaf-spine, we know that every leaf should be connected to particular spines. We also know that particular number of hosts within their racks is going to be attached to particular number of leaves. So far, what you see is full connectivity graph, known as underlay. What's interesting here, however, as you start deploying application, they don't particularly live on one host. We are talking about Kubernetes today. We are talking about really dynamicity of scale previously unknown. Stuff comes up, dies, moves without network knowing. So at any given point in time, you need to be able to say, my application is connected to this particular switches, and this is how you know what's the impact of outage, what's the impact of any change in the network. So it's important to be able at any point in time to connect your application, something that's really virtualized, not physical, into the rest of your infrastructure. And anytime it moves, being vMotion or VMware, or you deploy a new pod in Kubernetes, your system needs to reconciliate and update GraphView. Because the operational state should always be in sync with intended state. And again, think, you might have switches with different capacities. So 100 gig on one side, 10 gig on another side. If your application needs to consume 100 gig, probably you don't want to do vMotion on the part that's 10 gig. All of this is expressed as business logic, and system must enforce it. So this is the resulting schema. It looks kind of obvious, but think about how difficult is it to answer this very simple question. Show me all the links that carry application A to traffic. Imagine it's 5-7 stage network. How do you think about impact? So if one interface on leaf 1 goes down, how much my traffic is going to be affected? If one of the spines goes away, can my tenants, can my customers still achieve throughput I promised them? By having graph infrastructure, and we'll see how you can walk a graph, it's pretty standard. You can ask this presumably simple question, but actually very difficult question. In this case, you just see every link, every node. You can immediately understand the impact of any change. You can give an answer in tangible units, in gigs per second, in percentage, what is the impact of a change in my network. Let's talk about decomposition. So we've built this beautiful network that's multi-tenant, has many different layers, routing protocols. How do we deal with particular changes in particular subdomain? So what I'm going to show you is an internal tool that just represents your graph. So again, we are talking about same network as before. And on your left, you see a language called GraphQA that's used to traverse the graph. The intentions here is to show same network, so 4 leaves, 2 spines, but now we want to know all available paths. So logically, you could say 4 multiplied by 2 is 8, it's 8 link, but how do you logically and programmatically derive this? So we've got spines. We've got all interfaces that are out of spine. So logic of traversing the graph, you go either out direction or in direction. In this case, we go out. Now we got all the interfaces. And as we traverse the graph, we are getting all the right details. It just basic go out of relationship known as graph traversal. What's interesting here, the question is simple. Show me all the links between leaves and spines. Now you can also say, show me all the links where load is above 50%. Show me all the links that are between Cisco and Arista. Show me all the links that have optics that have power budget below a particular level. So by adding this metadata that is naturally added into your nodes in the graph, you can ask pretty much any question you can imagine. You can craft your questions based on context. For example, you see drop, but you don't understand why, right? Because we are in class, there's an ECMP, so you don't really know which path your flow has taken. However, if you see 7 optics at a particular budget and 8 at another one, probably the problem is there. So by creating these very specific queries in real time, you could get pretty much any data in near real time to figure out what's going on with your network. So in this case, the question is, show me all the links. So as you could see, you'll get exactly 8 links between 2 spines and 4 leaves. So let's talk about analytics. Again, this question came up a number of times during the presentations. How do we make sure we are asking for data that's relevant, that's in context, rather than just asking for everything? Looks familiar, right? So as an example, you see high-definition telemetry. Thanks to streaming telemetry today, you could get really, really high-definition stuff from Cisco, Juniper. You could go sub-second sometimes. You really get stuff that's crafted by an ASIC in terms of hardware telemetry, right? So we are getting the data. Finally, in industry, we got to the level of telemetry that we never had before. But consumption of the data is interesting. Now you see all 32 interfaces. Now you see all interfaces on all your leaves. What do you do with this data? You can look at it whole day. What does it mean to you? Very simple question. I have 32 interfaces. 8 of them are up, so they provide ECMP paths. Show me which of them are in balance. As we know, ECMP is implemented as per flow in order to preserve ordering of the packets. And in presence of fat flows, the imbalance could be rather significant. There are also technologies to change it. In later generation of merchant silicon, you can react on the next hop by changing it dynamically on fly based on depth queue. We see different vendors implementing it. So there really means to change this. You could go as simple as changing next hop in BGP, known as third party next hop, right? So you could do it, but you need to know what to do. Looking at the graph, you can do absolutely nothing because it doesn't give you actionable data. So in an intent-based system, you need to be able to build the query in real time since you've got all the information metadata in the graph, right? So in this case, we are interested about 8 interfaces that are between leaves and spines. So we know where to look. We can ask for counters. My business logic is saying that they are only overloaded if they're imbalanced more than 2 minutes out of 7. So again, here you're bringing your business logic into your network operations. You watermark the data, you start measuring, looking every 2 minutes intervals. More than 3 minutes, problem. Less than 3 minutes, irrelevant, don't even let me know. Since in this case, we say it's more than 3%, there's a problem, network is imbalanced. You could go do something about it. You could move workloads, you could use BGP to kick and rehash buckets. You could do many things, but at least you know there's a problem. So data has become actionable. So there are many questions. Would machine learning be really helpful in intent-based networking? What you see is 16-node Cisco network providing 110,000 customers, the counters. And if you utilize right techniques, you can actually group data points to the degree that you see that something has happened. In this case, BFD packets were filtered out. So interface or protocols on the interface would go down and load would change. However, on itself, you only know that something has happened. BFD went down, perhaps cable was removed, perhaps optic went down. However, it doesn't tell you who was affected, what's the business impact, and whether you really should do something about it. So I would say ML would be very useful in the bottom part, really trying to figure out what has happened, trying to bring it back and bind it to business intent. Because now, if you know this interface was down, by the way, there were these 20 customers whose traffic was traversing these interfaces, suddenly your data becomes actionable. Worst case, you'll go and tell your customer, sorry, you were screwed. Best case, you're out, you will move their workload, you could do something about it. Otherwise, it's just a piece of data that looks beautiful on the graph, but not very useful. So machine learning definitely has place in intent-based networking. However, it's not replacing, it's really complementary to the part where we humans cannot understand what's going on. So grouping significant number of data points, trying to correlate events that seems to be uncorrelated. And to explain how I see how analytics should work, since you know the intent, you could build a number of pipelines that would ask this particular important question. Show me only interfaces between leaves and spines. I don't care about any 100,000 interfaces. Show me what happened every 7 minutes or every 3 minutes out of 7. By reducing the amount of data, eventually you'll come up with high probability answer and say, it's an anomaly, I can remediate, or I can notify someone, or I can do something else. It's an actionable data point. Or you can decide, even though something is happening, it's probably irrelevant. I'm still within my SLAs, my customers are still happy, so be it. Maybe I just record it for future purposes. So ability to bind your analytical pipeline to intent is fundamental to get less data while deriving much more value out of it. And looking at the way you designed your network, it doesn't really matter whether it's 20 nodes or 20,000 nodes. The end result is exactly the same. You know what to look for. You know how to ask right questions thanks to metadata in the nodes to get right answers. So to conclude, basic automation, great stuff. Everybody is talking about it, but it solves problem. I mean, we know how to configure stuff. There's enough tools, both vendor-specific and open source, to do this. Single source of truth, we know that Kubernetes, for example, is outcome-driven. So you define your outcome, and your system will get to this. So we are getting there. There are systems that are doing it, and it's really good. It's what's needed for IBM to work. Dealing with data operations, however, is an extremely complex topic because of variety, network fails in all kinds of ways we don't predict, we don't know, right? So this is the most interesting part, and this is where I believe IBM is going to spend most of their time for the next 2-3 years. And this is where most of the art is going to come from. Questions, and thank you for your attention.
Hi, thank you. Thank you, Jeff. Great talk. I'm Srinidhi from Juniper Networks. I had a question about the single source of truth. So how would you prepare the single source of truth, and how would you update it and manage it? Is there a way to do it in an automated fashion and in a consistent manner? So as of today, there is no standardized way to express your intent. So if you look at most IBM systems available today, they usually provide a number of workflows that are reasonably intuitive for end user to express their intent. So I wouldn't say it's completely machine to machine. It's actually not. We, as industry, need to work on standardization of such interfaces, making sure that they're expressive enough to be able to consume this logic. So it's work in progress. And in addition to the intent, just the change management, like if something changes in the Kubernetes cluster moving somewhere, who looks at it and then updates the single source of truth?
So if you look at the model, usually it is sub-pub model, right? So particular subscriber will subscribe to particular information produced by particular consumers. In this case, Kubernetes management layer would be producer of such information, where someone on networking layer could subscribe to the information and deal with it. For example, you deploy a new pod, it's a well-known event, right? So you will notify your single source of truth about it. On the networking side, you might need to configure BGP session to get the reachability. You might need to provide more, more bandwidth. You might need to do something. So if data is normalized, an event is well understood by the system, you should be able to take this high-level event, new pod created, and translate it into low-level event, configure BGP session on switch B.
Thank you.
Pleasure. Any more questions? Thank you for your time and attention.